And now we're going to actually look at the forces at play with uniform circular motion. And as you remember from Newton's second law, we have the summation of forces equaling mass times acceleration. And therefore, we can assume, or we can know that this summation of forces acting radially or towards the center of the circle is equal to the mass times radial acceleration. And as we remember from our previous example, centripetal acceleration is equal to v squared over r. So that's going to be equal to mv squared over r. You just substitute the v squared over r for radial acceleration. So since in circular uniform motion, acceleration radial is directed towards the center of the circle, so is the net force acting on the object. So the classic example for this, as I mentioned earlier, is the ball being swung around in a circle in uniform circular motion. And we're going to have 2 points that are of interest. One at the top, whenever the ball is on the top, and one at the bottom. So as you may remember from our previous videos about this force tension, at the top we're going to have a force tension acting towards the center, as well as the force gravity, which is mg. And at the bottom we're going to have the mg and the force tension acting upwards, since force tension always acts towards the center of the circle. So now we want to find minimum speed of the ball to get over the arc. So that would be at the top of the circle. So now we're going to follow Newton's second law and then apply our equations and what we know about radial acceleration. So we know that summation of the forces radially, since they're acting towards the center of the circle, that's going to be equal to force tension 1 plus mass times gravity, which is our force gravity, which is going to be equal to mv squared over r, since we know it is moving in a circle and these forces are acting towards a circle, so we must set it equal to the radial acceleration, since the forces are acting radially. And in order for the ball to have a minimum speed, this means that force tension has to equal 0, because if force tension increases, since mass and gravity and radius are constant, they're not going to change. So our mass is constant, our gravity is constant, and so is our radius. The only thing that can change is the velocity. So if our force tension increases, velocity will also increase. So the way to achieve the smallest possible velocity is to have a force tension which is equal to 0. So now we have mg is equal to mv squared over r. We then can have v squared is equal to rg, and v is equal to root rg. And notice, the mass plays no role in the equation. No matter what mass we had, we would get the same answer for our velocity. You always want to look at your equation and notice what variables play a role and which variables don't play a role. So we're going to get velocity is equal to the root of our radius, which is 1.10 meters, times our gravitational constant of 9.81 meters per second squared. So our velocity ends up being 3.28 meters per second. And you can add tangent to the circle. Since we are writing velocity, which is a vector, you must add the direction of the velocity. So our second part of the question says the force tension of the cord, assuming v2, or the velocity of the object on the bottom of the circle, is twice that of the first velocity. So now what we're going to do is use Newton's second law, apply it to our radial acceleration, therefore using our radial forces, and just do the same thing. So I'm going to move over here. So we have our summation of forces acting radially, or towards the center or away perfectly from the center of the circle right here, is going to be equal to force tension 2 minus mass times gravity, which is equal to mv squared over r. Notice, I took force tension and subtracted mass times gravity instead of the force gravity minus force tension, since what I said was, as we already discussed, centripetal acceleration is towards the center. So the forces that act towards the acceleration are going to be spurring that acceleration, and the forces acting against or the opposite direction of the acceleration are acting against, so you'd subtract it. I gave an example in a previous video of the tug of war. If you are pulling towards the right side and the rope is moving to the right, you are causing that acceleration to the right. If another person on the left who's pulling in the opposite direction of the way the rope is moving is impeding that acceleration or impeding that motion. So our mass gravity in this case is impeding our radial acceleration, while our force tension is actually supplementing our acceleration. So now we're going to solve in terms of force tension. We're going to put mv squared over r plus our mass times gravity. Our force tension therefore is equal to mass v squared over r plus our gravitational constant. And notice that in this case, since we're solving for force tension, we're not ignoring force tension, we're not saying it's equal to 0. Mass does play a role in this case. So then you just plug in numbers, and since we said v2 is 2 times v1, you'd plug in 6.56 meters per second for v2. And that is your equation. You just plug in your numbers and can find your force tension. Now on to our next example. Oh yeah, and don't forget that acceleration or velocity on the bottom of the circle is always 2 times. We make the assumption that it's 2 times that of the top. So if you found the top acceleration, the next question is velocity, and what would the velocity on the bottom of the circle be? You just multiply by 2. So if it was 5 meters per second, you would assume that on the bottom would be 10 meters per second.